Now we'll come to the fourth module, which is stress concentration and notch sensitivity. What is stress concentration? Stress concentration can be defined as concentration of stress contour that happen in a body. That is, stress concentration is nothing but concentration of stress contours. By concentration of stress contours, what do I mean? Now consider the geometry like this, which is subjected to load P on both sides. Now when the load P is applied, the nominal stress which comes in the body given by sigma O, it's also known as sigma nominal, is nothing but P by A, that we have already seen. Now because these are the stress contours shown in the body, because of the change in cross section, because of the discontinuity, there's a change in direction of the stress contours. So and in this point of discontinuity, which is nothing but the change in area, here the discontinuity is nothing but the change in cross sectional area, sudden change in cross sectional area. The sudden change in cross sectional area causes concentration of stress contours at this region. If you see this tip portion, all the stress contours get concentrated at this location and results in a very high stress locally in this region. This is called the stress concentrations, and these discontinuities are also called stress raises. Discontinuities that happen in a geometry are also called stress raiser. That is, they raise the stress at those locations, and the region in which this happens, this occurs, is called area of stress concentration. So what happens in this region of stress concentration? So we have seen there is a concentration of stress contours, and what happens, the stress locally in this region becomes very high. That is given by a parameter called the stress concentration factor, called the theoretical or geometrical stress concentration factor, represented by letter K subscript T. The theoretical or geometrical stress concentration factor KT can be defined as the maximum stress to the nominal stress. That is the ratio of maximum stress due to discontinuity due to discontinuity of stress raises to the nominal stress value. This ratio is called the theoretical or geometrical stress concentration factor. Similarly, for the shear stress also, the theoretical stress concentration factor can be given as tau max to tau 0. And the stress this is called a theoretical or geometrical stress concentration factor because this KT depends only on the geometry. And it is independent of the material. Whatever be the material we use, the stress concentration factor will not change. The stress concentration factor depends only on the geometry of the specimen. Now, we have seen two types of loading, static loading and fatigue loading or cyclic loading. Now we will see the case of static loading. How do we apply the stress concentration in a static loading case? For static loading, we have seen two types of material, ductile material and brittle materials. So what are ductile materials? We know ductile materials are those materials in which the strain exceeds 5%. When the strain exceeds 5%, we call those materials as ductile materials. In ductile materials, when the stress concentration happens, what happens is, at those points of discontinuity, the stress becomes much higher, and the stress in those locations exceeds the yield stress. Exceeds the yield stress, causes plastic zone, and in turn leads to redistribution of stress. Results in redistribution of stress. Since the redistribution of stress is happening, the effect of this local stress raising is not critical. So in these cases we assume that Kt is equal to 1 because there is no effect of a high stress. Once the stress becomes high, the plastic zone happens and it causes redistribution of stress. It comes back to normal stage. Therefore, for static loading of ductile material, stress concentration factor is assumed to be 1. But what happens for brittle materials? Now we know that brittle materials are those materials in which the strain should be less than 0.05. The strain at failure is less than 0.05 or 5%. It's called a brittle materials. And we have already seen the stress concentration factor depends only on geometry. Sigma max by sigma nominal. In these brittle materials, the stress concentration factor is critical because this does not show any plastic zone here. It directly goes to failure. Therefore, when the concentration of stress is there, brittle materials are more liable to fail. So we can write that sigma max is equal to Kt into sigma O. So sigma O is a nominal stress which happens in the body. Once we know the load and the cross-sectional area, we can find what is the nominal stress. And depending on the geometry, we have the stress concentration factor. And once we know the stress concentration factor coming due to the geometry discontinuity, we can find what is the maximum stress coming in that location. So now we have seen how to apply the stress concentration factor for static loading for ductile and brittle materials. Now we have seen that the stress concentration factor Kt depends only on geometry. So how do we determine the stress concentration factor? We will see some common geometries. Suppose we have a specimen, rectangular body with a central hole of size, elliptical hole of size 2a and 2b. These are now we will find the stress concentration factor due to holes and notches. For the elliptical hole like this, now this body is subjected to a load P acting on both sides. Now we know the nominal stress is given by P by A. For such kind of a cracks or elliptical holes in a body, the stress concentration factor is given by Kt is equal to 1 plus 2a by b, where the major diameter is given by 2a and the minor dia is given by 2b. This is the stress concentration for the elliptical or circular holes. Now what happens for circular hole? We know that for circular hole A becomes equal to B. So the theoretical stress concentration factor Kt is equal to 1 plus 2a by b. Since A is equal to B, this becomes 1 plus 2 is equal to 3. Therefore for circular holes the stress concentration factor is 3. For circular hole, stress concentration factor is equal to 3. This we will keep in mind. Now we will see another different configuration of this elliptical crack in an opposite way. The orientation is changed by 90 degree. So here also this is 2a, this is 2b. Now in this case the ratio a by b is equal to 1 by 2, or b is 2 times a. So when b is equal to 2 times a, what happens to the theoretical stress concentration factor? This is nothing but 2a by b. This can be written as 1 plus 2a by b is also 2a. So this becomes equal to 1 plus 1 is equal to 2. So when a by b is equal to 1 by 2, we have Kt is equal to 2, or sigma max is equal to 2 times sigma nominal. In this case, sigma nominal is again sigma O is nothing but the nominal stress which is given by P by A. If P is the load acting here and A is the area of cross section, the nominal stress is given by P by A. The maximum stress which comes near the vicinity of this cracks is given by 2 times sigma O. Now in this body, in this geometry, if you take any cross section here, the stress will be P by A, which is uniformly distributed over the entire cross sectional area. The distribution of stress will be like this, but when you come near the crack, the distribution of stress becomes like this. When you go at a very large distance from the crack, this becomes equal to P by A, but at the vicinity of the crack, the stress will be KT into sigma naught or KT into P by A. So in this vicinity of this crack, the stress will be maximum is equal to KT into P by A. When you go away from the crack, the stress comes down to P by A. So that is the effect of stress concentration factor due to the holes. Now we will list out different cases. Now if A is equal to B by 2, stress concentration factor is equal to 1 plus 2A by B becomes 1 plus 2A by B. This becomes equal to 2, or we get sigma max is equal to 2 times sigma O, or nominal stress. Now when A equals B, as in the case of a circular hole, we know that this becomes equal to 1 plus 2 is equal to 3, or we have sigma max will become 3 times sigma nominal. And when A is equal to 2B, KT will be given as 1 plus 2A by B, and when A is equal to 2B, this becomes equal to 5, or the maximum stress is given by 5 times sigma O. Therefore we can see the stress concentration factor. A is equal to 2B is this case, and A is equal to B by 2 is this. So this case can be considered as A is equal to 2B, and this case is A is equal to B by 2. So in this case, the stress concentration factor is 5, whereas in this case, stress concentration factor is 2. Therefore this kind of discontinuity in the body, or this kind of holes in the body, is not at all acceptable, because the stress concentration factor becomes very high, or the maximum stress becomes much higher than this case. Therefore this case of holes still we can go ahead with, but this kind of a hole in the specimen cannot be accepted. So these are the stress concentration factor coming due to the elliptical and circular holes. Now we will see the stress concentration factor due to notches. So stress concentration factor due to holes, elliptical holes and circular holes we have already seen. So what is the stress concentration factor coming due to the notches? A is the distance of the notch from the surface, R is the radius of the notch. In such kind of case, the stress concentration factor KT is given as 1 plus 2A by R, where A is the distance of the notch from the surface. A is the distance of notch from the surface, and R is known as a notch radius. So in this case, the stress concentration factor is given as 1 plus 2A by R. I'll write it once more. KT is equal to 1 plus 2A by R. And the maximum stress in this case is given as nominal stress into 1 plus 2A by R. Where A is the distance of the notch from the surface and R is the notch radius. Now we know that the stress concentration factor is not at all good for our design. So whenever you have stress concentration or stress rises in the body, the stress concentration factor has to be included in the calculation of stress. How do we do the reduction of stress concentration? Because this stress concentration fact is not at all good for your design. So we have to try to reduce the stress concentration factor. How do we do the reduction? Reduction of stress concentration. One method of reducing the stress concentration is using fillets, and the other technique is using notches. So you may feel that notches are causing stress concentration. How we can reduce the stress concentration with notches? We'll show that here. Now if we take a specimen like this rectangular body with a circular hole, we know that stress concentration is happening because the stress contours get deviated like this. So this stress contours are deviating and causing concentration of stress in this location. The stress contours get deviated when very near to the circular hole. So how can we reduce this stress concentration factor is by providing additional holes. Now to reduce the stress concentration factor coming in this region, what we do is we put some additional holes on both sides of the major hole. What happens? The stress contours get deviated from this point itself and cause a smooth turn of the stress contours. So this is nothing but the reduction of stress concentration using additional holes. In this we are actually we are smoothing out the stress contour deviation. This is one method of reducing the stress concentration. Now what happens when we have a notch on the surface of the body? Here also the stress concentration is happening because it takes a sudden turn near the notch. The stress contour takes a sudden turn near the notch, therefore there is a concentration of stress occurring here. How do we reduce the stress concentration in this location? Same as in the hole, circular holes, here also what we do is we provide additional notches on the surface. This is the main notch available. We put additional small notches near the main notch so that we are slightly deviating the stress contours and we are reducing the effect of the change in stress contours. The stress contours get a smooth turn near the notch. This is by providing additional notches. By providing additional notch, we can reduce the stress concentration. This is one method of reducing the stress concentration by providing additional notch. Now what happens when we have a sudden change in geometry as we have seen earlier? There is a sharp change in geometry as shown here. Here also we have seen that the stress concentration is happening because of the sudden turn of the stress contours. So in order to reduce the sudden turn of the stress contours, what we can do is we can use fillets. We can slightly fillet that, give a radius to that sharp edge and reduce the effect of the sudden change in the stress contours. So the stress contours take a smooth path around the fillet and avoid the stress concentration. Stress concentration factor can be reduced this way by using fillets for a geometry with sharp contour change. Like if you have a sudden discontinuity in cross section area, the change in cross section area should not be sudden or should not be by a sharp edge. The sharp edge has to be filleted out like this. Filleting is nothing but giving a small radius to the sharp edge. Once you give a small radius to the sharp edge, the stress contours take a gradual turn at the area of discontinuity, thereby reducing the effect of stress concentration or in turn reducing the stress concentration factor. Now we see about the stress concentration factor for fatigue loading. Now for fatigue loading, the stress concentration factor, again stress concentration factor is a theoretical stress concentration factor, depends only on the geometry. But when we come to fatigue loading, before discussing about the stress concentration factor, there is another important term called notch sensitivity. We have to discuss this. The maximum stress in fatigue loading is given as Kf into sigma O, where Kf is called the fatigue stress concentration factor. Now we will see what is this fatigue stress concentration factor and how far it is different from the theoretical stress concentration factor. Because many materials the stress concentration for fatigue loading depends on the sensitivity of the material to notches. Like some materials will be highly sensitive to the presence of notch, and some materials will not be sensitive at all to notches. So the stress concentration factor for fatigue loading depends on theoretical stress concentration factor as well as notch sensitivity. That is fatigue stress concentration factor fatigue stress concentration factor Kf is a reduced value of theoretical stress concentration factor Kt, and the degree of reduction depends on the sensitivity of material to notch. Depends on sensitivity of material to notch, or also known as notch sensitivity. Therefore, the fatigue stress concentration factor Kf is given as 1 plus Q into Kt minus 1. So, important relation where Kt is the theoretical stress concentration factor. Theoretical stress concentration factor. Kf is the fatigue stress concentration factor. And Q is the notch sensitivity of a material. So, notch sensitivity is a material property and a theoretical stress concentration factor is a geometry property. So, that materials can be divided into different classes based on this notch sensitivity. That is, some materials will be fully sensitive to notch. So, two cases we can consider where Q is equal to 1, that is materials that are fully sensitive to notch. In such kind of material, the fatigue stress concentration factor will be given as 1 plus Q into Kt minus 1. This will be equal to, where Q is equal to 1, so this becomes equal to Kt. For materials which are fully sensitive to notch, the fatigue stress concentration factor becomes equal to theoretical stress concentration factor. Now, second class of material is the other extreme where Q is equal to 0, that is materials which are fully insensitive to notch. Materials fully insensitive to notches. Such materials, the fatigue stress concentration factor will be 1 plus Q into Kt minus 1. This will be equal to 1. Therefore, for materials which are fully insensitive to notch, the fatigue stress concentration factor is taken as 1, and for the materials that are fully sensitive to notches, the fatigue stress concentration factor is taken as the theoretical stress concentration factor. So, we can summarize as follows: Q is equal to 1, then Kf is equal to Kt, or Q is equal to 0, then Kf equals 1. Or the notch sensitivity can be written as Kf minus 1 by Kt minus 1. Similarly, for shear also, Q shear is equal to Kfs minus 1 by Kts minus 1. This is the notch sensitivity of the material for fatigue. So, the stress concentration factor for fatigue depends not only on the theoretical stress concentration factor, but also depends on the notch sensitivity, or how sensitive a material is to the presence of notch. Okay, having learned so much about the stress concentration factor, the theoretical stress concentration factor and the fatigue stress concentration factor and notch sensitivity, we will try to solve one problem. A plate made of steel 20C8 having an ultimate tensile strength of 440 Newton per mm square is hot rolled and normalized condition is shown in this figure. It is subjected to completely reversed axial load of 30 kilonewtons. The notch sensitivity factor can be taken as 0.8, which is nothing but the Q, and the expected reliability is 90%. Factor of safety is 2. Then determine the plate thickness for infinite life. Ka is given as 0.67, Kb is 0.85, Kt is 2.51, and Ke is 0.897. Now we have to find what will be the thickness of the material for infinite life of the body. Now first of all, since they have asked for infinite life design, we should know what is the endurance limit of the material. So SC dash is given as 0.5 times SUT, that will be equal to 0.5 times 440, that is nothing but 220 Newton per mm square. This is the endurance limit of the laboratory value of endurance limit. Now actual endurance limit for this application will be given as SC is equal to Ka Kb Ke into SC dash, which is nothing but Ka is given as 0.67 into Kb is given as 0.85 into Ke is given as 0.897 into SC dash is 220. So this will be the endurance limit of the body. How much it will be? 0.67 into 0.85 into 0.897 into 220. That is nothing but 112.38 Newton per mm square. This is the endurance limit of the body. Now for infinite life design, for infinite life design, the stress in the body should be less than SC. Now what is the maximum stress in the body? Maximum stress is given as Kf into sigma O, where Kf is the fatigue stress concentration factor. Stress concentration. So what is the value of fatigue stress concentration factor? We know that theoretical stress concentration factor Kt is given as 2.51 and the notch sensitivity is 0.8. So Kt is 2.51, Q is equal to 0.8. So what will be Kf? 1 plus Q into Kt minus 1, that's equal to 1 plus 0.8 into 2.51 minus 1. This is how much? 1 plus 0.8 into 2.51 minus 1. This is nothing but 2.208. Therefore the maximum stress is given as Kf into sigma naught, that is nothing but 2.208 sigma naught. And what is the normal stress? Normal stress is given by P by T into what is the area available? In this location the diameter of the notch is 10 mm. Therefore in this location what is the area available? Area available is 50 minus 10, that is 40 into thickness. So P by thickness into 50 minus 10, or I can say P by 40. T is the nominal stress. Therefore we can say 2.208 times nominal stress should be less than SE, or sigma O should be equal to SE by 2.208. And what is SE? 112.38 Newton per mm square divided by 2.208. This is nothing but 112.38 divided by 2.208 is equal to 50.89. And since the factor of safety is 2, therefore sigma naught should be less than 50.89 by n, that's equal to 50.89 by 2, that's equal to 25.44. Therefore nominal stress should be less than or equal to 25.44 for the infinite life of the body. And what is nominal stress? Nominal stress we have already seen here is equal to P by 40T. Therefore, P by 40T should be equal to 25.44. And what is P? P is equal to 30 kilonewtons or 30,000 newtons. Therefore, we can say T is equal to P by 40 into 25.44. That's equal to 30 kilonewtons, 30,000 divided by 40 into 25.44. 30,000 divided by 40 into 25.44. That is equal to 29.48 mm. Therefore, the thickness of the body should be 29.48 mm for infinite life of the body. So, this way we can find out what is the, we can design the components given the value of Notch sensitivity and the theoretical stress concentration factor. So, this is one example. We will try to solve one more problem. We will solve another problem shown here. This is in the concept of stress concentration factor and Notch sensitivity. A component, a machine from a plate made of steel 45C8 having UTS of 630 Newton by mm square is shown below. It is subjected to completely reversed axial force of 50 kilonewtons. The expected reliability is 90% and factor of safety is 2. Determine the plate thickness T for infinite life if the Notch sensitivity factor is 0.8. Ka, Kb, Kc, Ke and Kt values are given. Now, again here also we are going to design it for infinite life. Therefore, we should know what is the endurance limit of the material. Laboratory endurance limit is given by 0.5 times SUT. That is given as 0.5 times of 630. That is nothing but 315 Newton per mm square. And what is SE? SE will be equal to Ka, Kb, Ke into SC dash. That is nothing but Ka is 0.75. Kb is given as 0.85 into Ke is given as 0.897 into SE dash is given by 315. This will be how much? 0.75 into 0.85 into 0.897 into 315. This will be 180.12 Newton per mm square. This is the endurance limit of the material. And for this kind of a loading, the maximum stress is given as Kf into sigma O, where Kf is equal to 1 plus Q into Kt minus 1. The Notch sensitivity factor Q is given as 0.8 and the theoretical stress concentration factor is given as 2.27. Therefore, the fatigue stress concentration factor can be written as 1 plus 0.8 into 2.27 minus 1. That is equal to 2.016. The fatigue stress concentration factor. Therefore, sigma max is equal to 2.016 sigma nominal. Therefore, for infinite life design of the material, the maximum stress should be equal to the endurance limit, less than or equal to. That is, maximum stress should be less than or equal to SE by N, where N is the factor of safety. So, for design condition can be taken as sigma max is equal to SE by N. So, what is sigma max? Sigma max is equal to 2.016 sigma O is equal to SE is 180.12 divided by factor of safety is 2. And what is sigma nominal? Sigma nominal for this condition is equal to P by A, that is P by 50 into T, because we can take 50 or 100, because since we are interested in the maximum stress, stress will be maximum in this location compared to this location. So, we can take the nominal stress as P by 50 into T. T is the thickness of the material. So P by 15 T is a nominal stress. Therefore we can say 2.016. Therefore 2.016 into P by 50 T is equal to 180.12 by 2. Or we can say T is equal to 2 into 2.016 divided by into P divided by 180.12 into 50. The P is equal to 50 kilonewtons, that is 50,000 newtons. We have seen already here P is equal to 50 kilonewtons. So substituting that, we get 2 into 2.016 into 50 kilonewtons, that is 50,000 newtons divided by 180.12 into 50. This will be the value of thickness in mm. So what is this? 2 into 2.016 into 50,000 divided by 180.12 into 50. That is nothing but 22.39 mm. Therefore, the minimum 22.39. Therefore, the minimum thickness should be 22.39 for infinite life design of the component. 22.39 mm. For the component to withstand infinite number of cycles. So this way we can do the design of components if we know the stress concentration factor clearly. So the fatigue stress concentration factor, unlike for static loading, depends not only on the theoretical stress concentration factor but also depends on the factor notch sensitivity, which is nothing but the factor which tells how sensitive a material is to presence of notch. Once we know the theoretical stress concentration factor, which depends only on geometry, and the notch sensitivity factor of the material, we can calculate the fatigue stress concentration factor. Once we know the fatigue stress concentration factor, we can design the components to withstand any number of cycles. So with this, we come to this end of this module on fatigue stress concentration factor due to holes and notches.